Good afternoon, this is Schweitzer, and we're going to do a little PowerPoint today on calorimetry. So, what is these are some of the topics that we're going to be discussing today in calorimetry. Um, what are some of our main topics here? Okay, well, what is calorimetry? Um, what does a calorimetry system look like? How can I calculate heat transfer with a calorimeter? What are some practical uses of calorimetry? So in this situation, let's just take a look at a couple examples. All right, what is calorimetry and how is it used in everyday life? So in general, okay, let's think about this, okay? You have a system and it's exiting energy. We kind of have two ways that we generally look at this, okay? One is method one, which we're going to just call calorimetry. And this is going to require some ingenious scientist or engineer to come up with a unique system to do this, but essentially a system is exiting energy in all directions. And all we're going to do is simply develop or build some device around the outsides that's going to simply collect all this energy. Okay, so that's one way. You can imagine that kind of idea. I mean, if you have a campfire, and you stand around the outside of the campfire, you feel the heat come off. You're collecting heat. If you want to get all the energy come off a campfire, well, you need to be kind of all around, right? You need to be able to find some way to collect all the energy in all directions. It's never perfect, but it's kind of the idea, right? Um, so what's the other way? Okay, just a brief description of this. And this is kind of coming off the idea of conservation of energy. That energy cannot be created nor destroyed. So technically, this is a different idea. Way is that if you knew how much energy was here before, energy before, and all of a sudden this thing gave off some energy, and it could also take in energy, doesn't really matter. And then you do, after it's done, you look at the energy afterwards, then if energy cannot be created or destroyed, it's a finite item, then you could track these two systems, system before and then the system after. And this one would be before. So if you were to subtract these two systems, the net difference or change in energy would be the amount of energy the system lost or gained. If it's losing, again, we have this graph looking like this, which like that, and that's kind of what we're talking about. Energy before, energy afterwards, and the net difference is your energy change. All right, but this video is more on calorimetry, which is we're literally just going to collect the energy from the outside. All right, well, how would you do that? Um, these are some examples of this. Literally, um, how do I build a device that would collect energy? It's got to be something that's like all around it, okay? And we need something to collect it. Now, this idea here, in order to determine an unknown, you must have a known to compare it to. And a lot of times we refer to this as a known collector. And when I say collector, I mean something that is like, okay, what's known about it? And really what's known about it is lots of stuff. Okay. So in this situation, when something collects energy, call it Q, depending on how much mass is there, um, its change in temperature, and its specific heat, we can figure out how much energy something collects. Now we got a lot of complicated idea here where we may burn something inside here and then it gives off energy, and this is my known collector around here. Of course, if you're adding in energy, you'd have to, you know, you'd have to subtract that amount of energy off. This is really how you're going to do something with food. They're going to drop in a pellet of food here. You could take a Whopper, for example, and get all the water out of it because that's not providing any energy, and just get a pelletized version of a sample of food, burn it. But if you're taking it, you gotta subtract off that particular energy you add, and then all the other energy that comes off is from the pellet of food burning. Either way, so this is a kind of a complicated example, but notice we're all around the outside of it, and the water that's in here would have a known specific heat, and that is 4.18. Now, really, when I'm talking about a known collector, then that's really what I'm referring to. What's known about it is the specific heat. So I need more than that. Obviously, if I'm collecting something in here, I need to know the mass of the water, the collector. I know the temperature change of the collector, hence the thermometer. I know the specific heat of the collector. Now here would be an example, just doing something solid. Now again, this is not as useful, maybe it's this one, depending on what you want to do. This is just solid block. We have one of these at school, and it has, again, certain amount of logistics. Q equals mass times change in temperature times for heat. First of all, it's aluminum, and it has a mass of 500 grams. It has a change in temperature. Well, you'd need to be able to put a thermometer in here, okay, and figure that out. So that would be delta T, something you'd want to be able to figure out. And then the heat of this thing is aluminum, is just 0.9. Okay. So this guy, you drop something in, it radiates energy or it gives off, and the block warms up. And that tells us how much energy we have. So why is this our known collector? Because we know that it's 0.9 is my specific heat of this guy. And that's joules per gram per Kelvin or degrees Celsius. All right, so what about this guy? This is one that we might use in high school. It's really not pretty good, actually. You use a double insulated cup, um, and we just have a mixture in here of water. We could drop something in. So again, this is not as useful, okay, but it's a simple idea. We have a known collector. We need something that is going to collect the energy, and it needs to be known. So we really need to know all the stuff about it in order to say it's a known collector, but the specific heat is the one thing that we really have to know because everything else we have a means to collect, on our own physically. But, okay, so a little bit about how we physically do it. All right, well, what about just a simple transfer of energy? Okay, can we do this? So a lot of times when we're doing a scientific experiment, we need sort of a proof of concept. Okay, like something works. All right, can I collect energy in a transfer? Now this example, you might say, well, that's kind of boring. What are we going to do with that? Well, there's lots of examples of things that we're always looking to transfer energy all the time. Okay, and we could sit here and talk energy transfer is super important. Things warming up too much, but this is just a simple example. A more everyday example might be even just, let's say, in a car. Okay, just a quick little example of energy transfer, just in case you're wondering, how would you ever do this? Okay, well, if you have a car versus, let's say, a semi. Okay, now a semi, of course, as you know, they gotta stop just like everybody else. All right, so you got a semi which has got a great big load on it. So when a semi stops, it stops just like a car stops. And all the energy of movement, which is called kinetic energy, is going to get transferred into thermal energy, heat. And that's going to be right inside those wheels. There's a little rotor and a brake, a rotor with a little brake pad on it. And it's literally, as the wheel goes around, it starts to pinch that rotor and then creates heat. Well, what do you think happens to the brake pads and the brakes and that chunk of metal there? It warms up. So if you put car brakes on a semi, the only difference is that the heat is going to build up and cause it to literally melt. So that's an example of energy transfer that is really important to know, that when something collects energy, how much will it raise up in temperature? Now again, a lot of that might be the same materials that they have, but maybe the brake for a semi has just got a much larger mass, so that for a given energy transfer, the change in temperature isn't as great. Okay. So, all right, so a simple example here, just proof of concept, can I collect energy as I transfer it? So I want to know, for example, I have a block here, and my objective in this little thing here is just a little side objective, is just to determine the specific heat. Objective, okay, this is a pretty common example of um, a demonstration we do in class all the time. Okay, so I have a block, and I'm going to try and find the specific heat of that block. And I'm going to kind of show my proof of concept here. And we're going to get a good look at specific heat. So on this thing, we would weigh the block. And my block I typically have now, it has a mass of, I weigh it, we put on a scale, and 125 grams. Okay, I've heated the block to 100 degrees Celsius. It's pretty easy to do. I can boil it in water. All right, so I get an insulated cup with some water in it. Okay, the water has a temperature of 23 degrees Celsius. Okay, I have a mass of water of 100. Let's measure that out to be exactly 125 grams of water. Okay, so from here, I'm going to point out I have this little table here. This is a pretty interesting table. We've seen tables like this before, but again, known collector and unknown. The known, I'm going to be dropping this block into the water, and the block is going to be radiating energy to the water. Therefore, the water is going to get hotter and the block's going to get cooler. The water is going to lose energy. The water is going, so this is going to be my block. I like to write that up there. This is my water. So this guy is going to lose energy. This guy's going to gain energy. Okay. So ideally, these would be equal in our perfect system. All right, so let's try this out. Let's put in our data we know. The mass of the water. Well, it's 125 grams. 125 grams. Now, these don't have to be the same. But in class, I typically try and get them pretty close. A lot of times, the mass of the water is just to be determined by how much I can fit in the container. Okay, temperature initial of the water is 23 degrees Celsius. Now that's going to be 23 plus 273 is 692. 296 Kelvin. 296 Kelvin. Okay, this guy is going to be water, and the water is 273 plus 100, and that's going to be 373. Okay, 373. All right, so you drop it in, and energy transfers. Now, water has a known specific heat of 4.18. It drops in, and you let it fizzle around a little bit, and the temperature change is about, ends up, this thing warms up to about 20, typically about 29 degrees, something like that. So this thing went to 29. Okay, let's do it again. 273 plus 29. Now you notice this thing only went up 6 degrees. Okay, so I could add 6 to this guy, and that would give me 302. Because a degree Kelvin is the same as a degree Celsius. But 9 to 11, 12, so 0, and then 3. 302. All right, which means this guy also, since they're in the same container, this thing will radiate energy to the water until literally the temperatures of the block equals the temperature of the water. So these are now equal, 302 degrees. Now, keep in mind, each of this row is just one of these formulas. And if I know of all the variables, if I'm missing one of them, I can figure the whole thing out. So my general plan here is to determine the energy that the water collected. That equals the energy that the block lost, and then I can solve for the specific key of the block. Now again, this doesn't have a ton of practical uses for us. Just a proof of concept, can we collect energy and figure something out? Okay, so let's solve this out. I'm using this formula. So Q equals the mass, which is 125, times my change in temperature. I'm going to subtract these two, which is just, as I mentioned, 6, and times 4.18 of my known collector specific heat. Now, before I calculate that, notice a pretty interesting example here. The water changed 6 degrees. How much did this guy change? Looks like it changed 71 degrees. That's an excellent example of specific heat. Notice that we have the same masses. This guy changed 6 degrees. This one changed 71. That's a great example that this amount of energy needed to raise 1 gram of sample 1 degree Celsius. The amount of energy needed to raise water up a degree is much larger than this guy. Sometimes we refer to that as heat capacity. Got a large heat capacity. All right, so let's solve this out. What does this equal? Grab our calculator, and we got 125 times 6 times 4.18, and I get 3,135. So this is 3,135 joules of energy. If you forget what units we have here, you can always take a look at the specific heat, which is normally given on the problem, and it'll have the units on it. Joules per gram degree Celsius or Kelvin. Now that equals this guy as well. So these are both now the same value of this. Now this is negative because it's losing energy. This will be a negative temperature change. So when you're plugging in, you can actually take the negatives off, but I'm going to leave them on for now. So negative 3135 equals 125 times a negative 71 times unknown value C. What does C equal? All right, so just divide out. Divided by 125 divided by the temperature change. I get 0.35. Okay, 0.35, and that's joules per gram degree Celsius. So this is just one example of the math that we would use in this type of system. And you should see your workbook for more examples of this type of stuff. But let's move on to maybe a couple more things here. Things that we might use in the future, like things we would want to use this for. All right, so here's an example where we have a food system. Okay, this is a lab that we typically do in honors chemistry. you could burn a nut here, and the energy goes up here. So how would we use this table? This table's not super useful at this point. So my known collector is my water. Okay, so this is my water. And let's say I have 100 grams of water in here. Starts out at 25 degrees Celsius, ends at, I don't know, 90 degrees Celsius. It's got a 4.18 joules of energy per gram degree Celsius. Okay, then Q. Okay, I could solve for that. So I could figure out how much energy the nut gave off. Okay, so what would I do with that? Okay, well, it turns out that well, every nut's a little different. So can I say that every nut has that amount of energy? Maybe all my nut didn't burn. Maybe, so there's a couple things we can do here. One, I could do simply a ratio, and that is all we ever look at as far as packaging on labels. I mean, if I burn a nut that's twice as big, I get maybe twice the energy. So maybe I'm looking at a ratio of energy, okay, which is Q divided by, let's say, mass of nut. And that gives me Q per gram. And that is very similar to what they do for packaging. What they do is they take their Q per gram, they assign a certain number of grams, depending on the substance, and they call it a serving. And they're going to give you the energy, they're going to call it a calorie, or if you're in Europe, a kilojoule, calories per serving. And that is what we're looking for. That's what's on the package. Now, if we look at one more small thing here, I'm not going to talk too much about this now. Just one more thing I'll notice here is that, just point out quickly, is that this particular table has some usefulness. But does the nut have a mass? Sure. We could have used it right here to get our ratio. Does it have initial and final temperature? Not really. Does the nut have a specific heat? It's not really doing anything for us here. This table really is not, it's falling short here. Okay. This still works well for one side, but the other side, not so much. So it's a good table, but use it for what it's worth. So my last thing I have here for you is just an idea of something that we might be looking for in the future. Okay. And that is, okay, what about how much energy does a reaction give off? Okay, energy of a reaction. Now the reaction could be simply eating, some sort of a food item. Okay, if you were to eat, a slice of pizza, how much energy is in a slice of pizza? Okay, well, it really kind of depends how much pizza you eat. Okay, if you eat one particular slice of pizza, all right, then you get X amount of energy. But of course, if you eat two of them, or if you were to eat three of them, then of course you get more energy. And that's kind of how chemical reactions work. Let's say I want to know how much energy X, okay, when X goes to Y, how much energy is given off on this process. And of course, this we would call an exothermic process, because energy is on the product side. Okay. Well, how much energy does it give off? Well, that's like saying, if I eat pizza, how much energy do I take in? Well, it depends how much pizzas you eat. So really, it's a cycle. Our chemical reaction really is a cycle. And how many times we cycle through that process determines what energy we give off. And that cycle, energy, one time through the cycle, this is called delta H. And that really is Q, which is the energy. That energy has to be collected, and it typically comes from Q. It goes mass times change in temperature times heat of the collector. Either way, but that energy is just energy. It's like saying how much energy is in one slice of pizza. Q, 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 okay? And that is per, we call per mole. And that would be per mole of the reaction. So if 1 mole of this goes through and produces 2 moles of this, it'd be for either of them. So delta H would be the amount of energy Q per 1 mole of X, or the delta H is the same Q per 2 moles of Y, because they're connected by the stoichiometric ratio. So just a little hint in our next video, we'll look a little bit more at how you actually solve something like this out. Well, thank you very much.